Alright, this is 5.5 problem number 5, and we're looking at u substitution, and so I'm going to explain what goes through my head when I'm trying to pick u substitution. So what I'm looking at here is I'm looking at this term, 5 plus 3 x to the 1 half. Now if I took the derivative of x to the 1 half, I would end up with something x to the minus 1 half, which would mean we would have a square root of x in the denominator if for the derivative of our u, if we pick this as u. And you'll notice here that this square root of x is in the denominator, so that is a minus x to the minus 1 half. So because of that, I'm going to pick for my u, I'm going to pick the term inside here, 5 plus 3 x to the 1 half. I'm not going to bring the squared in there because I want the derivative of this to include x to the minus 1 half. I am going to include any constants in there because that's going to clean up my problem. Because remember, we take the derivative of a constant and they go away. So now we know what our u is going to be. So now we take the derivative of u with respect to x. The derivative of u with respect to x is going to be 5 goes away, and then we end up with 3 halves x to the minus 1 half. And now what we're going to do is we're going to go ahead and mix some things around. So I'm going to multiply the dx over. I'm going to prove that du equals 3 half x to the 1 half dx. And now I've got a 3 here, right? And I've got the x to the, x to the minus 1 half. You see that there? And so what this actually looks like is 3 over 2 root x dx, and we're starting to notice the 3 in the root x. The 3 over the root x is going to match up here. Let's go ahead and multiply the 2 over. So 2 du equals 3 over root x dx. And so now what we're going to do is we're going to say, okay, so our u, we picked our u as 5 plus 3x to the 1 half. So this is our u right there. And now we're looking for our du. Well, our du is this part right here, because it includes the dx and the 3 over root x. And then we're going to do our substitution. So we can rewrite this as the square root of 1 over u squared, right, because u is squared. And then what is du, or what is 3 over root x dx? Well, 3 over root x dx is 2u. So I need to multiply that by 2 du. And then I can simplify. I can pull the 2 out front because it's a constant. And what I end up with is u to the minus 2 du. And then at this point, I could just use the power rule. And I'll end up with u to the minus 1 over minus 1 times 2. And don't forget our constant of integration, the plus c. And then we can rewrite this as 2 negative 2 over u, right? Because u to the minus 1 is the same as u in the denominator. And then we're going to plus c. Then what we can do is we can resubstitute what our u was in the first place, which is 5 plus 3x to the 1 half. So we can substitute that in 5 plus 3x to the 1 half. And that is our, so we substituted it, solved it in its simpler form, and then resubstituted at the end in order to get it back into its original form. And because I haven't hit this in any other video, I'd like to talk about the constant of integration and why we need it whenever we take an indefinite, or definite integral for that matter. Okay, so what's important to remember, okay, so let's say that I have 5x cubed plus 6x squared plus 4, and I'll say that's equal to y. Now if I take the derivative of y with respect to x, using the power rule, I'll get 15x squared plus 12x, and then the 4 goes away, right? So in taking a derivative, we're actually destroying information. We've destroyed information. Now, if I go ahead and I take the antiderivative, so I go ahead and take the antiderivative of 15x squared plus 12x, alright, let's do an indefinite integral. What's going to happen here is, using a power rule, I'll end up with 15x to the 3 over 3 plus 12x to the 2 over 2. And this looks like what we started with, 5x to the 3 plus 6x to the 2. It looks like what we started with, but the 4 is gone. We actually have no way of interpolating the 4. So we destroy things with derivatives. So when we take the antiderivative, or an integral, we have to respect the fact that we actually destroyed a vertical shifter in this function. Graphically, why that is because, as you could imagine, with a graph like this, we can have more than one graph that has the same derivative. As a matter of fact, there's infinitely many graphs that could have the same derivative. The only difference, because their slopes are shared at every given x, they'll have the exact same slope. So they'll always have the exact same slope at every given value of x. The only difference they'll have is they'll be shifted. They'll be shifted in the y direction, apart from each other. And that's what the plus c is. It's a vertical shifter. So, and the only way that we can solve for c is if we have some initial condition, or unless we know the original function. But anyways, I just thought that'd be good to cover, just to explain why the plus c is so important. It's very easy to forget, but it's very important for later on, especially in classes like differential equations and stuff like that. Alright, well, I hope this was helpful, and I'll see you next video.